All right, so you guys sent in a ton of stuff about non-locality.
Yeah.
And this is one of those concepts that just makes you rethink.
Absolutely.
Like how we even view space and time.
It really does.
We're talking about particles potentially communicating faster than light, what's going on with black holes, and even like, what does here even mean, you know?
It really challenges those assumptions that we kind of take for granted. You know, like we assume that things have their own separate existence, that they can only interact in very limited ways.
Yeah. Okay. So let's break that down a little. When we say locality.
Yeah.
I mean, we're really talking about like two main ideas.
Right.
So first, the idea that things are separate, right? Like my coffee mug isn't suddenly going to merge with your, bookshelf across the country.
Exactly. That's that separability, that objects have their own distinct identity, even when they're separated by, large distances.
Yeah. And then the second idea is that things can only affect each other through like direct contact or signals that travel at a reasonable speed.
Right.
Not exceeding the speed limit of the universe.
Exactly. The speed of light.
Yeah, the speed of light. So no, teleporting furniture or instant messages across the galaxy.
At least not according to classical physics, right?
Right.
Yeah.
Then we get to modern physics with quantum mechanics, general relativity, and suddenly things get a little
messy.
Yeah, messy, bendy.
Yeah, it's like the rules of the game changed a little bit.
Yeah, and it's so fascinating that even Einstein, who you would think would be all about locality, actually played a key role in developing quantum mechanics, which introduces this really wild concept called entanglement.
Yeah, entanglement. It's really, really bizarre, but also very cool. It's where you have two particles that become linked, and whatever happens to one instantly affects the other, even if they're light years apart.
It's like they have like a cosmic cell phone or something.
Yeah, right. Like they have some sort of secret communication channel that transcends space and time.
And Einstein actually debated with Niels Bohr about this.
Right.
Saying that entanglement suggested spooky action at a distance.
Right. He did not like that idea at all.
Spooky action. I mean, that sounds like something out of like a movie, but...
It does sound like science fiction, but there's actual scientific evidence to back it up.
Yeah, like they actually did experiments.
Oh, yeah. Tons of experiments. And actually, one of the most important pieces of evidence comes from what's known as Bell's theorem, which was developed by a physicist named John Bell decades after Einstein. And it's a bit complex, but to kind of oversimplify it, imagine you have two people flipping coins. And if the choice of which hand they use to flip the coin influences the outcome in a way that, violates our traditional understanding of probability, it suggests that there's some kind of non-local connection between these two coins.
So it's like the coins are like talking to each other.
Yeah. It's like they're coordinating their flips, even though they could be miles apart or even, light years apart.
Yeah, I mean, it
is very weird.
Seriously mind-boggling.
It is. And, Bell's theorem has been experimentally verified many, many times, showing that this spooky action, as Einstein called it, it's not just some theoretical quirk.
Right.
It's actually how nature works.
Okay, and so what does that even mean for us?
It's profound. I mean, if we can't rely on this idea of locality, then it really challenges our understanding of cause and effect. It challenges our understanding of the limits of what's possible.
Yeah, I mean, it makes you wonder if we've just been looking at the universe like through, I don't know.
Too narrow a lens.
Yeah, too narrow of a lens.
Assuming that everything is local.
Right, and it has to be, neat and clean and...
Right, cause and effect, everything neatly separated.
Yeah, but maybe it's all kind of tangled up together.
Maybe it's more of a cosmic web of interconnection.
That's where things get really weird.
It does get really weird. And, some physicists have even proposed alternative explanations because they're not comfortable with this idea of non-locality.
Right.
So they've proposed things like, maybe time isn't as straightforward as we think.
Okay.
And maybe events in the future can actually influence the present.
Whoa.
Yeah.
Are we talking time travel here?
Yeah, it's called reverse causation.
Okay.
The idea that the future can influence the past.
Like the end of a movie can influence the beginning.
Exactly.
Okay.
And then there's another idea called the many worlds interpretation.
Okay.
Which suggests that every time a quantum measurement is made, the universe splits into multiple parallel universes, each with a different outcome.
Whoa. So there's like an infinite
number of possibilities.
Number of me's out there making different choices.
Potentially, yeah. Every decision you make could be branching off into a new universe.
Okay, and so then there's also the idea that...
Right, and then there's superdeterminism.
Superdeterminism.
Which is the idea that free will is an illusion.
Oh, wow.
And everything is predetermined from the start.
So we're just like actors following a script?
Essentially, yeah. And this would eliminate the need for any faster-than-light communication because everything would already be set in stone.
So basically we've got backwards time travel.
Yeah.
We've got infinite parallel universes.
Right.
And we've got a universe where everything is already decided.
Yeah, pick your poison.
Yeah, pick your poison. But either way...
Non-locality seems to be a fundamental part of reality.
Non-locality is here to stay.
It seems that way, yeah.
So this is already blowing my mind. But the thing is, it might not even end there.
It doesn't.
Right.
Non-locality may actually go beyond the realm of these tiny particles.
Okay, so where else does it show up?
Well, even Einstein's theory of gravity, general relativity, hints at some pretty non-local features.
Okay, so like what? Give me an example.
Well, for example, it allows for the possibility of wormholes.
Okay.
Which are these theoretical tunnels through space-time that connect distant points, potentially enabling faster-than-light travel.
So those instant messages
maybe
across the galaxy...
are not entirely out of the question.
Not entirely out of the question?
Yeah, we don't know for sure if wormholes exist, but general relativity allows for them.
Okay.
And it's not just wormholes.
Yeah.
General relativity also tells us that gravity warps space and time.
Right.
So it can actually blur the lines between what we consider here and there.
Yeah, so our sense of location gets a little fuzzy.
It does. The universe is a lot stranger than we often give it credit for.
Yeah, and I think that leads us to an even more mind-blowing idea.
It does.
Which is this concept of emergent spacetime.
Emergent spacetime, yeah. This is where things get really interesting.
Yeah, emergent spacetime, which is...
the idea that space and time might not actually be fundamental building blocks of reality, but rather they emerge from something deeper, a deeper level of reality that may not even be spatial.
So space and time are like...
they might be emergent properties.
like an illusion.
In a way, yeah. It's like, imagine a giant network of interconnected points.
Yeah.
And the connections between these points define the spatial relationships.
Okay.
So at very high energies,
yeah,
this network is super, super dense. There's no concept of distance, really.
Okay.
But as energy decreases, these connections become more sparse and organized.
Yeah.
And what we experience as space emerges from this network.
So it's like space is a pattern in something else.
That's a great way to put it. It's like a pattern that emerges from a more fundamental underlying structure.
That is wild.
It is wild. And there are other theories, like matrix models, which envision the universe as this massive network of interacting particles.
Okay.
Each represented by a matrix, which is basically a grid of numbers.
Right. That encode information about that particle and its relationship to other particles.
So it's like each particle has its own little ID card.
Exactly. It's like a cosmic ID card.
With all the data. Like,
with all the information encoded in it.
Encoded in it, and then somehow these ID cards, like...
and the relationships between these particles, as encoded in the matrices, give rise to what we perceive as space and time.
Create space and time.
Yeah, it's a very strange and very beautiful idea.
And it really challenges, like, our fundamental understanding of reality.
Absolutely.
If space and time aren't even real.
Right.
What is?
It's a deep question.
Yeah.
And it's one that physicists are still grappling with.
It's fascinating how these ideas are being developed. And I'm really curious to see what's next, where we go with this.
We're just at the beginning of this exploration.
Yeah.
And I think there are a lot of exciting discoveries yet to be made.
Absolutely. All right. Well,
yeah, definitely dive deeper into this when we come back.
Sounds good.
But for now, I need to...
take a break
and
process all this.
Wrap my head around all this.
Absolutely.
Because it's pretty mind-blowing.
It is mind-blowing.
All right, we'll be back in a bit.
All right.
Okay, so, wow, my brain is like still trying to wrap itself around this whole idea of emergent spacetime.
A big one.
Yeah, it's a big one. But it seems like there's real science behind it, right?
There is, yeah.
But I'm wondering, like, how do we actually test these theories? I mean, we can't exactly create a black hole in a lab.
Right.
To see
directly testing how space-time behaves.
These theories is incredibly difficult.
Yeah.
But there are some really interesting possibilities. For example, some physicists believe that if space-time is emergent, we might actually be able to create tiny artificial wormholes in the lab.
Whoa, whoa, whoa.
Yeah.
Mini wormholes.
Mini wormhole.
It's a lab.
Using advanced quantum technologies? Okay, now that's an experiment I would love to see.
Right.
So,
could we, like, send messages through them?
Well, that's still very speculative. Yeah. Even if we could create these mini wormholes, sending messages through them would be incredibly difficult.
Okay.
It would require an insane level of control over quantum systems.
So maybe no wormhole internet anytime soon.
Not yet. The fact that we're even considering this possibility shows just how far we've come.
I mean, that's incredible in itself.
It is, yeah.
So our sources also talked about using lasers to search for evidence of extra dimensions.
Right.
How does that even work?
So there are experiments that are looking for tiny variations in gravity over very short distances.
Okay.
The idea is that if there are extra spatial dimensions curled up at a microscopic level, they could subtly influence the gravitational force.
Okay.
And we might be able to detect those deviations.
So it's like we're looking for
these tiny ripples.
Tiny ripples, subtle variations.
In the fabric of space-time to see if there's these extra dimensions.
Yeah, it requires incredible precision.
Right.
Pushing the limits of technology. But that's what's so amazing about science.
But that's what's so cool about it.
It's always pushing the boundaries.
Yeah, and it's fascinating how, this whole idea of emergent space-time really challenges our assumptions about reality.
Right.
Right. I mean, we've always thought of space and time as like...
Right, as the backdrop.
The stage on which...
the fixed...
The universe plays out.
Right.
But what if it's not the stage at all?
What if it's something else?
But like something that emerges from a deeper level of reality.
Yeah, it's a fundamental shift in perspective.
Yeah, it's a big one.
It is.
And even if we discover that space-time emerges from something else... it doesn't mean that our current understanding of physics is, like, wrong. Right.
Not necessarily, no.
It's more like
It's like we're adding another layer of complexity.
Adding another layer.
A deeper level of understanding.
Like we're constantly zooming out and getting...
Zooming out, getting a wider view.
A wider view of the cosmos. And realizing how much more.
Yeah, and realizing that things are much more interconnected than we initially thought.
And that's what makes this so exciting, right? We're not just... like tweaking the equations, we're like...
Or potentially rewriting our understanding of...
reimagining the very...
fabric of reality.
Fabric of reality.
It's pretty amazing.
And that's what makes this whole discussion so fascinating, right?
It is, yeah.
We're really, like...
Challenges everything we thought we knew.
Questioning everything.
Yeah.
So if space-time isn't fundamental, I'm kind of curious.
Yeah.
What does that mean for our understanding of causality?
That's a great question.
Like the idea that every event has a cause.
Right, because our understanding of cause and effect relies on this linear sequence of events.
Right.
One thing leading to another.
Right.
But if space-time itself is emergent, maybe that linear order isn't as fundamental as we think.
So it's like we're looking at a timeline, but maybe the timeline is just...
Right, maybe the timeline is just one way of looking at a much more complex, interconnected web of events.
Okay, I think I'm starting to get that.
So
before we go too far down the rabbit hole, I am curious about those specific theories of how space-time could emerge.
Right.
So like quantum gravity and matrix models.
Yeah, let's dive into those a little bit.
Give me the rundown.
Okay, so quantum gravity, as we touched upon earlier, envisions space-time as this network of interconnected nodes. And at super high energies, these nodes are incredibly densely packed, like a swarm, no real space to speak of. But as the energy drops, the connections between nodes thin out. And what we perceive as space emerges from this network.
So it's kind of like a social network.
Yeah, that's a great analogy.
Where the more connections you have, the closer you are to other people.
The closer you are, and as the connections thin out, you get this sense of distance.
Right, and that thinning out could be related to like the cooling of the universe.
It could be related to the cooling of the universe after the Big Bang.
So as the universe cooled, like the energy density decreased.
Yeah.
And the network
the network went from this super connected spaceless state to a more organized spatial one.
So like water transitioning from a liquid to ice.
Exactly.
The universe went through like a phase transition.
Going from...
from this spaceless state to one where space emerged.
Okay, and so that's quantum gravity.
That's quantum gravity.
What about matrix models? Those seem even more
Matrix models are even more abstract.
Yeah, abstract. They envision the universe as this massive network of interacting particles.
Okay.
Each represented by a matrix.
Right.
Which is essentially a grid of numbers that encodes information about that particle.
Okay.
And its relationships to other particles.
So it's like each particle has its own...
It's like a cosmic passport.
Cosmic passport with all its information.
With all the information encoded in it.
Exactly.
And somehow all these passports together create the fabric of space-time. It's a wild idea.
Wild, yeah.
But it's a very powerful one.
So how do you even go from numbers in a grid to like something that feels like space, right?
Yeah.
With
That's the million-dollar question.
It's 3 dimensions.
Right.
The passage of time.
We don't have a definitive answer yet.
Right.
But one idea is that the matrices represent what are called pre-geometric entities.
Okay, pre-geometric entities.
So these aren't spatial in the way that we normally think about space, but they have the potential to arrange themselves into a special structure.
So they're like the raw ingredients of space.
That's a great way to put it, yeah.
Waiting for the recipe to come along?
Yeah, and the recipe might be encoded within the relationships between the particles as represented by the matrices.
Okay, I'm starting to see how, like, mind-bending this is.
It is, yeah.
I mean, we're talking about
challenges every day.
Questioning the very nature of space and time.
It really does.
Which is, I mean...
It's the foundation of our reality.
It's like the foundation of reality, right?
Yeah, and it's not solid.
And we're like shaking that foundation.
We're realizing that the foundation might be a lot more wobbly than we thought.
Yeah, and that's kind of like...
It's unsettling.
Unsettling in a way.
Yeah.
But also kind of exciting.
It is exciting, yeah.
So as we go deeper into this, are there like any guiding principles? Any key takeaways?
I think one key takeaway is that even though these theories might seem very radical, they're rooted in solid mathematics. They're not just random speculations.
So it's not just physicists making things up.
No, they're being rigorously developed.
Okay.
Tested by some of the brightest minds in the field.
So it's like... It's
serious business.
Serious science.
It is, yeah.
Okay, what else should we keep in mind?
I think another important thing to keep in mind is that emergent space-time theories aren't necessarily about invalidating everything we know.
Okay.
Just as Einstein's theories didn't completely wipe out Newtonian physics, emergent space-time could provide a deeper, more nuanced understanding.
Okay.
Without completely overturning our current knowledge.
So it's an expansion?
It's an expansion.
Not a demolition.
Exactly. It's like adding a new dimension to a map.
Okay.
Showing us hidden pathways and connections that we couldn't see before.
Yeah, I like that analogy. And I think maybe the most important thing to remember is that this whole exploration of emergent space-time is a journey.
It is a journey, not a destination.
Not a destination.
There are still many questions to be answered.
Right.
New discoveries are being made all the time.
It's a really exciting time.
It's a very exciting time to be following this field.
Yeah, and it feels like
we're on the precipice of something.
It feels like we're on the verge of a revolution.
Yeah.
In our understanding of the cosmos.
Yeah, you've definitely piqued my curiosity.
Good, I'm glad.
Because I really want to know where this all goes.
Yeah, me too.
So speaking of, mysteries and all that, in the next part, we're going to explore some of the most,
the most mind-blowing...
mind-blowing implications.
Yeah, we're going to get into the really weird stuff.
Of emergent space-time.
Black holes, the Big Bang, even the possibility of other universes.
Buckle up, everybody, because...
things are about to get wild.
It's going to be a wild ride.
All right, so we spent some time now exploring this concept of non-locality and this mind-bending idea of emergent space-time.
Yeah, it's... definitely a lot to process.
It really is. But I'm starting to see how these seemingly abstract concepts could help us understand some of the biggest mysteries in the universe.
Yeah, absolutely.
We're talking black holes, the Big Bang.
Yeah.
Even maybe other universes. It's like we've got this ultimate cosmic puddle.
Yeah.
And emergent space-time might just be the missing piece.
I think you're right.
So let's dive into that a bit.
Okay, let's do that.
Black holes have always been like a source of fascination, but also bewilderment.
They really are fascinating.
Right. These regions of space-time.
Yeah.
Where gravity is so intense that nothing, not even light, can escape.
Not even light. It's pretty mind-boggling.
Yeah. It's always seems like
Right.
the ultimate dead end.
A cosmic dead end.
Where the rules of physics.
Yeah, where everything breaks down.
Yeah. So how does emergent space-time change our perspective on black holes?
Well, one of the biggest challenges in physics is trying to reconcile general relativity, which describes gravity, with quantum mechanics, which governs the behavior of particles. And black holes really push this conflict to its limits because they involve incredibly strong gravity and quantum effects all tangled up together.
So it's like the two theories are battling it out.
It's the ultimate showdown between two of our most fundamental theories.
In the arena of a black hole.
Yeah, and it's a battle that we haven't quite figured out the outcome of yet.
And this clash leads to... like some major paradoxes.
It does, right? The black hole information paradox.
Information paradox, where it seems like information just disappears.
Yeah, information seems to disappear when it falls into a black hole, which violates the laws of quantum mechanics.
Okay, so where does the information go?
That's the big question.
Does it just vanish?
Right. Does it get destroyed?
Or is it somehow preserved?
Yeah, and this has been a source of debate for decades.
I mean, it seems like a magic trick.
It's like a cosmic magic trick.
Where something just...
disappears without a trace.
Disappears.
And that's where emergent spacetime might offer a solution.
Okay.
If spacetime itself isn't fundamental, but emerges from a deeper structure.
Okay.
It's possible that information falling into a black hole isn't truly lost.
Right.
But gets encoded within that underlying structure.
So it's like the information is transferred to a different hard drive.
That's a great analogy, yeah.
That's operating at a level of reality.
At a deeper level.
Don't perceive.
Beyond our usual perception of space and time.
Okay, so emergent spacetime could potentially solve the information paradox.
Yes, resolve that paradox.
What about the singularity?
Yeah, what about that singularity?
At the center of a black hole.
Right, that point of infinite density.
Where everything
breaks down.
Yeah. Does emergent spacetime?
So the singularity, and how we think about that,
is one of the most perplexing aspects of black holes.
Yeah, it's where everything seems to collapse.
It's a point where our current laws of physics simply break down.
Right, so does that mean...
And if spacetime is emergent?
That it's not a...
The singularity might not actually be a literal point.
Real place.
Yeah, not a place you can visit.
Yeah, but...
But rather a kind of boundary or transition zone.
An edge.
Yeah, an edge of the map, beyond which... our usual notions of space and time no longer apply.
We don't know what happens.
Right, it's like reaching the end of a video game world.
Yeah, it's like...
You hit an invisible barrier, and the rules of the game no longer apply.
The rules no longer apply. And emergent spacetime suggests that the singularity might be a similar kind of boundary.
Yeah, it's fascinating how,
it is.
This new perspective.
It's a whole new way of looking at things.
Gives us a whole new set of tools to understand.
Yeah, it gives us a new framework.
These complex objects.
For understanding these really extreme environments.
And maybe even the origin of the universe itself, right? The Big Bang.
The Big Bang, yeah. The biggest mystery of them all.
Yeah, I mean... Yeah. It's like the ultimate origin story.
The ultimate origin story.
But we're missing
But the first few chapters?
The first few chapters.
I was missing.
Does emergent spacetime offer any clues?
Well, if spacetime is emergent, it might not have actually existed in the very early universe.
Okay.
Instead, there might have been what's called a pre-geometric phase.
Okay.
A kind of quantum foam.
Right.
A realm of pure possibility from which space-time crystallized.
So it wasn't just matter and energy exploding into space.
Right. It wasn't just stuff exploding into a pre-existing space.
It was space itself emerging.
It was the very fabric of space and time emerging from this deeper level of reality.
It's like the universe created the stage as the play began.
That's a great way to put it.
That's incredible.
Yeah, and it opens up possibilities that we couldn't have even imagined with a classical view of space-time.
So what else could this reveal?
Well, I mean, it could even have implications for the existence of other universes.
Okay.
If space-time isn't fundamental...
Are we talking about,
It's possible that different regions of this pre-geometric structure could have crystallized into separate, self-contained universes.
Like parallel universes.
Yeah, like a vast cosmic ocean of potentiality with bubbles forming and expanding.
Okay.
Each bubble, a unique universe.
So not just...
with its own laws of physics, its own history.
Like different versions of ourselves making different decisions.
Right, not just parallel universes in that sense.
But completely...
entirely different universes.
Yeah, different universes.
Yeah.
Okay, and so could we even detect...
Well, detecting other universes is a huge challenge.
Yeah.
But some physicists believe we might be able to see indirect evidence of their existence.
Okay, so like what?
For example, if our universe collided with another universe in the distant past, it might have left behind subtle imprints in the cosmic microwave background radiation.
So we're looking for, like, bruises, like
cosmic bruises,
echoes of these
ancient collisions.
Wow, and even if we find them, like,
it's likely that these other universes would be forever beyond our reach.
Right, but even the possibility...
But the very idea...
expands our cosmic horizon.
Understanding of the cosmos.
It's like realizing that the Earth isn't the center of the universe.
Right.
But just one small planet orbiting an average star.
Yeah.
In a vast galaxy.
And now we're realizing
that galaxy,
that is one of billions.
Our universe might just be...
in a potentially infinite universe.
One bubble in a sea of...
And now we're realizing that even that infinite universe might just be one bubble in a cosmic foam of multiverses.
Wow, it's humbling and awe-inspiring all at the same time.
It is. It really is.
So,
yeah,
we've gone from questioning the nature of space and time...
it's been quite a journey.
...to the possibility of a multiverse.
It's been a wild ride.
What does it all mean for you, the listener?
Yeah, that's the big question.
If space and time aren't what we thought they were?
Right. What does it say about our place in the universe?
What does it say about us?
And could our everyday experiences be echoes of a deeper, interconnected reality?
Yeah, a reality we're only beginning to glimpse.
We're just starting to understand.
Yeah, so we'll leave you with that.
Yeah, some food for thought.
To ponder.
Absolutely.
As we wrap up this deep dive into non-locality and emergent spacetime.
Thanks for joining us.
Until next time, keep exploring, keep questioning, and keep your mind open to the fray.
Yeah.
Keep an open mind.
Infinite possibilities of the cosmos.
Absolutely.